In this video, we're looking at solving exponential equations using what we know about logs. And so in this first problem, in this first equation, I want to isolate that exponent. So I'm going to divide both sides by 5, and I end up with 2 to the power of 3x equals 8/5. Now, we can do whatever we want as long as we do it to both sides. And so I'm going to take the log of both sides, as in log base 2 of 2 to the power of 3x and log base 2 of 8/5. Now, I picked log base 2 very specifically because of the fact that I have a base of 2 right here. And I did it for a reason. So log properties, I know that in a log, when I have a power right here, that 3x, I can move it to the front. And so I have 3x times log base 2 of 2. Now, I did log base 2 to both sides because I know what log base 2 of 2 is. So log base 2 of 2, the question is what is the exponent that goes on there? Well, if I put this in exponential form, I have this, 2 to the power of x equals 2. And this is an understood 2 to the power of 1, which means x equals 1, or this whole thing right here equals 1, which means this equals 1, which means really this is just 3x. So I have 3x equals log base 2 of 8/5. Now let's be very clear. Log base 2 of 8/5 is ugly. It is a very ugly, irrational number, and it's just, that's all I can say about it. It's an ugly, irrational number. But since I'm solving for x, I divide both sides by 3, and what I have is x is equal to this ugly, irrational number, log base 2 of 8/5 over 3. And the cool thing is that that's it. That's what x equals. X equals this super ugly, irrational number divided by 3. And that's how we leave it. You could type it into a calculator and get a decimal equivalent, but it's irrelevant for us. We just know that it's an ugly number divided by 3, and that is nicely where we get to leave it. This next problem, pi to the power of 1 minus x equals e to the power of x. There are different versions of this problem, as in like different numbers plugged in there, but this works out in a kind of pattern, and until you've done it a few times, it is really kind of scary. And so just know that going in, that this one has a lot of work to it, but it does fit a certain pattern, and you'll see that pattern repeated in problems similar to this. Both my x's are in exponents, and so similar to how I did log base 2 on this previous problem, I'm going to do a log. Now, I'm going to use natural log. I have e right here, and so I'm going to take the natural log of both sides. So that's the natural log of pi to the power of 1 minus x equals the natural log of e to the power of x. Now, there's a couple things I'm going to do here, log properties. So one, similar to how I did log base 2 of 2, and that's simplified out of the problem, when I have natural log of e, that literally means log base e of e to the power of x. So you move that x down front, log base e of e is 1, which means log base e of e to the x, or natural log, this right here, natural log of e to the x. In the end, it comes down to just be x. This part simplifies out nice and neat. Now, the left-hand side does not clean up nice and neat, but I can use log properties to know that this exponent comes out front to be a coefficient. So I have 1 minus x, make sure you have that in parentheses, times the natural log of pi. Now, pi is an irrational number before we were taking the natural log of it. It's an irrational number on top of an irrational number. It is super irrational. It is ugly to the nth degree. So knowing that it's ugly to the nth degree, just remember that. It's ugly. It's an ugly number. Natural log of pi is just an ugly number. So just know that as we go through this, that we're looking at that as just an ugly number. Now, I have the natural log of pi being multiplied by 1 minus x. I am now going to distribute this in. And it's not obvious, but there's a very specific reason I'm doing that, because I need to clean this up. And so I have lateral log of pi times 1 is the natural log of pi. And I have the natural log of pi times negative x is negative x times the natural log of pi. And all of that is still equal to that x on the right-hand side. Now I'm doing this because I want to get my x's together. So I'm going to add x times the natural log of pi to both sides. And this will, in a second, you'll see that it actually cleans up kind of nicely. So that simplifies out, and I'm left with the natural log of pi, just that ugly number, is equal to x plus x times the natural log of pi. Now, you may be thinking, this doesn't look all that cleaned up, but what I can do to this right-hand side is actually I can factor it a little bit. I can factor out a common factor of x. There's an x in the first term and there's an x in the second term. And when I factor that out, x divided by x is 1, and x times pi times the natural log of pi divided by x is just the natural log of pi. And what I have now is I have my x combined into a single iteration of x. So I have on the left-hand side, the natural log of pi is equal to x times 1 plus the natural log of pi. Well, the cool part is x is almost by itself. If I divide both sides by this parentheses, 1 plus the natural log of pi, I have exactly what I want, which is x equals. This simplifies out, and I have on the right-hand side just that plain x. The left-hand side, I have this giant pile of crap, ugly number, divided by 1 plus that ugly number. But the best part is I'm fine with it. I have x equals some number. Ultimately, that's just some number. Happens to be super ugly, but it's just some number. So this is a puzzle, and we have to navigate it. So when I look back up here to my original is right here. That is the original equation. I had x's on this side, and I had x's on this side. I used my log properties to get access to them. I took the natural log of both sides, which simplified this right-hand side to just be x. The left-hand side, I used my log property to put that 1 minus x out front. But to get to that x, I had to distribute into that parentheses, and so I did. That allowed me to move this term over to the right-hand side. You can see that right here. And once I had them both together, I took out the greatest common factor of x, and then I was able to divide away that ugly piece left over. And in the end, I have x equals the natural log of pi over 1 plus the natural log of pi. Last problem. And this is also a classic kind of problem that can be really confusing, but it fits a pattern, and once you begin to recognize this pattern, it'll make your life a whole lot easier. So what you'll notice is I have 25 to the power of x minus 8 times 5 to the power of x equals negative 16. I have two different bases, and that should be a red flag. We can't have two different bases like this. We need to be working out of the same base. And to do that, we're actually going to realize that 25 is just a power of 2. 25 is the same as 5 squared. So really what I have is I have 5 squared to the power of x minus 8 times 5 to the power of x equals negative 16. And this, if I use my log powers on top of powers, that's 5 to the 2x power minus 8 times 5 to the power of x. And I'm being really methodical, but I want you to see something kind of cool. I'm basically going to the trouble of doing this. And what you'll notice is I now have both in terms of 5 to the power of x. So in theory, all I did was I switched these places. I just did it methodically. And I went 5 squared to the power of x to 5 to the power of 2x. And then I pulled it back to being a power on top of a power, 5x squared, 5 to the power of x squared. And I did that because what I really want you to see is if I do a little bit of substitution, if I say y is equal to 5 to the power of x, what you're going to notice is this. This problem actually becomes this. Y squared minus 8y equals negative 16. Now, why does this matter? This matters because this just became a quadratic. It was actually always a quadratic, but it was hard to see. Now, if I add 16 to both sides, I have y squared minus 8y equals 16. Sorry, I botched that. Plus 16 equals 0. And what do we do with quadratics? Well, we factor quadratics. Two numbers that multiply together to be 16 and add together to be negative 8. Well, that's y minus 4 and y minus 4. And that looks pretty simple. And so because of the same thing, I really only need to solve this once. Y minus 4 equals 0. But at this point, I'm going to say, please do remember that we're not dealing with y. It's really 5 to the power of x. And so what I have then is I have 5 to the power of x minus 4 equals 0. And if I go to solve this, what I end up with is 5 to the power of x equals 4. Now to get to that x, I need to get rid of this base. So I'm going to do the same thing to both sides. I'm going to take log base 5 of both sides. Now, as we've seen a couple times in this video, log base 5 of 5 simplifies out, and I'm left with x. And on this right-hand side, I have this weird thing, log base 5 of 4. That's an ugly irrational number. It's just an ugly number. However, I have x equals a number. That is my answer. This right here is my answer. That is the ugly number that satisfies this equation right up here. So the first thing I had to do was manipulate this a little bit so that it looked like this, and you can see where you have the squared term and you have the power of one term. We use a little bit of substitution, that right there, and that allows us to see it really clearly as a quadratic. We solve the quadratic all the way down to here. And then we say, you know what? I'm really not worried about y. I'm worried about 5 to the power of x. So we did some substitution back in, and then we solved it out. And it just so happens to be an ugly number, and it's okay. This is our answer. So these last two types of problems, this one that was a quadratic, and this one up here that dealt with some incredibly ugly numbers, those are classic problems that you will see. Don't be afraid of them. Just know that they're coming, and that as you practice them, these patterns will become much clearer.